On this video, we will discuss the RNA world hypothesis, a geologic perspective on life's origin. I am your host, Professor Gilbert Bernhardt, for this episode of A Science Moment. 4 billion years ago, Earth was a dynamic planet of volcanoes, tidal flats, and shallow seas. In that shifting geologic environment, the first building blocks of life began to assemble. Today we explore how geology shaped the earliest chapter of biology, the RNA world. When we talk about the origin of life, we often imagine molecules floating in a mysterious primordial soup. But as geologists know, early Earth was not a uniform broth. It was a dynamic planet full of volcanoes, impact craters, tidal flats, evaporating pools, and newly forming oceans. These environments shaped the chemistry that eventually produced life. One of the leading ideas that connects geology with biology is the RNA world hypothesis, the proposal that before DNA, before proteins, life was built around a single remarkable molecule, RNA. Life today depends on DNA to store information and proteins to do nearly all the work. But DNA can't copy itself without proteins, and proteins can't form without DNA. So where could the first biological system come from? Geology provides part of the answer. Early Earth offered mineral surfaces, wet-dry cycles, and energy sources that could help simple molecules assemble into something more complex, RNA, capable of both storing information and catalyzing reactions. It fits this environment perfectly. RNA solves that puzzle. It can store information like DNA, but also fold into catalytic shapes like proteins. This makes RNA an ideal candidate for life's earliest chemistry. But the key insight for geologists is this: RNA doesn't have to form spontaneously in open ocean water. Instead, it forms far more readily on mineral surfaces, especially clays. Experiments show that clay minerals, especially montmorillonite, common in volcanic ash alteration and floodplain environments, can, 1, absorb and concentrate organic molecules, 2, line them up in favorable orientations, and 3, catalyze the formation of RNA chains. In geologic terms, clays act like reaction platforms. Their charged surfaces and massive surface areas bring simple molecules together, helping them link into longer RNA strands, making it one of the strongest geology-biology links in origin of life research. Imagine early tidal flats or ephemeral ponds, wet during high tide or storms, then drying under the sun. So geology provides part of the answer. Early Earth offered mineral surfaces, both wet-dry cycles and energy sources, that drove condensation reactions that may have helped simple molecules assemble into something more complex, like RNA, capable of both storing information, catalyzing reactions, and it fits this environment perfectly. Once RNA molecules form, some would fold into shapes capable of catalyzing chemical reactions. These are called ribozymes. A few of these early ribozymes could help RNA strands copy themselves. The moment any molecule could copy itself, even imperfectly, Darwinian evolution began entirely within a sedimentary or hydrothermal landscape. Variants that copied faster or survived longer would increase. Over time, networks of RNA molecules may have formed primitive metabolic systems. This is the heart of the RNA world, a stage in Earth history when life was not cellular but molecular. As the RNA world evolved, RNA began to interact with amino acids, another class of molecules common in early Earth settings. Short peptides formed, offering better catalysts than RNA alone. Eventually, proteins became the main workhorses. Later still, DNA, which is more stable than RNA, took over long-term information storage. But the machinery that makes proteins today, the ribosome, still uses RNA at its core. It remains a fossil of the RNA world inside every living cell. Geology provides strong support for the RNA world framework. Abundant clay minerals, hydrothermal systems, creating reactive environments, and organic-rich meteorites delivering building blocks. These are all part of Earth's early geologic record. The RNA world hypothesis does not answer every question, but it ties biology tightly to geology. Minerals acted as catalysts. Tidal cycles drove reactions, and the energy and materials of a young planet provided the setting where chemistry became life. From clay minerals on ancient shorelines to hydrothermal systems deep in the crust, the geologic processes you learn in physical geology were not just shaping landscape, they were shaping life itself. The RNA world hypothesis, a geologic perspective on life's origin, was written, produced, and hosted by Gilbert Bernhardt. Music Darkness of Night was composed and performed by Brady Booth.